Hello, everyone. I'm Osman, and I welcome you all to our last seminar of the year being presented by Zakieh. Zakieh Mohammadi is a PhD candidate in geotechnical engineering at the University of Calgary, specializing in permafrost and regions engineering. She holds a bachelor's and master's in civil and geotechnical engineering from Bu Ali Sina University in Iran. Her master's research focused on mechanical properties of fine-grained soils and the influence of pore fluid characteristics. Currently, under the supervision of Professor Jocelyn, Zakieh is developing predictive frameworks for thaw settlement in permafrost regions, addressing the impact of climate change on infrastructure. She also contributes to permafrost characterization and assessment as part of the mining team at WSP Canada. So now I hand it over to Zakieh for her presentation.
Thank you, Osman, and thank you everyone for joining today's seminar. Today, I'm going to present my work on developing a framework for evaluating soil settlement in permafrost regions. This was the work that I have done as part of my PhD project, and this topic is crucial as permafrost degradation significantly impacts infrastructure stability. Let's dive in. In this slide, you can see a quick overview of what I will be covering today. I will start with the introduction and motivation for this research, followed by objectives and methodology we use. And from there, I will explain the framework structure and also some key components of the framework, including a component focused on large-scale assessment and components more related to site-specific evaluation of soil settlements. And then we have conclusion and future works. Let's begin with the motivation behind this research. As you know, permafrost is covering about 50% of Canadian lands, and it plays a critical role in providing stability for infrastructure in northern regions. But with climate change and the Arctic warming, which is even faster in northern regions compared to the globe, permafrost is dying, which leads to significant stability and serviceability challenges for infrastructures. In these slides, you can see a soil-related hazard map for continuous permafrost regions in Canada. It shows projected hazard potential by 20 under RCP 4.5, which is an optimistic emission scenario. But even for this scenario, we can see there are substantial portion of these areas classified as having either high or moderate hazard potential, which are shown in darker shades of red on the map. And as you can see, the high hazard potential areas are home to cities and major infrastructures like transportation networks, pipelines, and mining operations. And they are also likely to be candidates for future development in these regions. So this means that both maintenance of the existing infrastructures and planning for future development will be impacted significantly by permafrost degradation. And to better understand this impact, we need to probably take a closer look at the challenges facing the designing of foundation in permafrost regions. So one of the key challenges for infrastructure in permafrost regions is soil settlement. And soil settlement happens when thaw-sensitive permafrost, which is a permafrost that changes in volume or loses its strength after thawing, begins to thaw. Soil settlement is influenced by two main factors. Actually, it's a product of these two factors, soil strain and changes in permafrost extent. Soil strain mostly depends on ground material and ice content, and changes in the permafrost extent is affected by baseline permafrost condition and alteration caused by climate change and human activities. Traditionally, the foundation design in soil-sensitive regions was based on using passive methods. These methods aimed to keep permafrost frozen, therefore to avoid thawing, and as a result to prevent settlement. But with the accelerating pace of climate change, these approaches are becoming less visible and more increasingly expensive. So these changes shift the strategies toward using active methods, which are based on designing foundations that can accommodate changes in permafrost condition. And one of these changes is soil settlement. So to effectively implement active designs, it's crucial to accurately predict soil strain and also the extent permafrost changes. With this background provided, the overarching objective of my research project was to develop a comprehensive framework for soil settlement evaluation, because we believe this is something that becomes more frequently needed in the future with the changes in the climate condition and with the changes in the strategies that we might use during foundation design. And to achieve this, we focus on several key goals. We tried to identify and centralize tools that are useful for predicting soil settlement. And we also tried to improve if there was a gap or there was shortcoming. We tried to improve prediction of soil settlement by developing new tools. And we also focus on improving our ability to identify soil-sensitive regions, and finally to create workflows that allow for evaluation of soil settlement across multiple scales. To achieve these objectives, we use systematic methodology. This methodology was designed to address the gaps in existing soil settlement tools and create new ones where needed. So the process began by reviewing and centralizing existing tools, and then which this literature review helped us to identify the gaps and try to address those gaps. Particularly, we could see that tools tailored for coarse-grained and highly organic soils were we had fewer tools for these two type of soils. And we also, as part of this project, we compiled and digitized water data on soil settlement, because this was something that we needed for addressing the gaps. And using the compiled data and the identified gaps, we were able to develop new tools and also evaluate the performance of some of the existing ones. And I will explain like different steps that we have taken in more details in the upcoming slides. So in these slides, you can see a kind of simplified version of the framework structure. At the top, you can see input data starting with coarse large-scale information on the left and moving toward more detailed site-specific data on the right side of this diagram. We have coarser scale data here and then finer scale of data, more site-specific data on the other side of this diagram. And you also can see that the different components of the framework, and we mainly divide them into two major categories. The first is the one that are used for large-scale vulnerability assessment, which help with identifying soil-sensitive regions using regional scale data. And then we have more kind of site-specific assessment, which is focused on estimating soil strain based on index properties that are collected during site investigation. So they rely on more site-specific data. And also, during the kind of site-specific evaluation, we can improve the data that we have, like the amount of the data and also the complexity of the method that we use to have more refined assessment. So this is just an overview, and many workflows need to go into these components to create the kind of the complete version of the framework. So with this overview in mind, let's take a closer look at different components, and I will show literature review, like what was already available and what was our contribution for creating these components. So the first component is large-scale evaluation of vulnerability to Thaw settlement. This component was integrated into this framework because we believed that it is useful during the feasibility studies. Like, the aim was to provide something that's useful during the feasibility studies. And in terms of resources available that can help conducting this type of assessment, we have large-scale vulnerability assessment, which are mostly produced in a map format, and they show the hazard map, soil-related hazard map for large scales, typically relying on coarse-scale geospatial data and climate data. And here you can see an example by Yurt et al. That is kind of a reference to see the resolution of the data, the resolution of the results, and also the scale of the map. Checking these maps can be useful as a first step to have a broader context of Thaw settlement risk for a region. But these maps sometimes lack the ability to be applied in a smaller scale. And most of the existing approaches mostly focus on modeling changes in the active layer thickness, and they use ground ice to represent Thaw strain. They are kind of overlooking the role of soil texture in defining Thaw strain. So we decided to take a look at these gaps and try to develop some methods to address these gaps. So to do so, we developed a new method which integrated soil texture into the evaluation of Thaw settlement hazard more accurately, and we developed a Canada-wide Thaw settlement vulnerability map using this approach. We also leveraged approaches used in developing the existing maps to create workflows, like to extract the approach and then to create workflows and resources that use those approaches and resources that they can provide to create workflows for conducting evaluation during feasibility studies. So the approach that we developed was mostly focused on evaluating Thaw strain. As I said, there are many maps and approaches that are focused on accurately representing the changes in the permafrost extent, or to compare the existing or current active layer thickness versus projected active layer thickness. And they kind of overlooked the Thaw strain part of the Thaw settlement. So we focused on this component, and we incorporated 3 key variables to assess what we call susceptibility to settlement. So we use ground ice content, surfacial deposit unit, and bedrock type. So the idea is this is some sort of assessment that you can do during a desk study evaluation. So we wanted to rely on publicly available resources. And we use the analytical hierarchy process to assign weights to each variable based on their importance in defining Thaw strain. So we were able to create an index called Thaw settlement potential index, and then we created a map of this index for Canadian permafrost, as you can see here. To create this map, we simplified the changes in the active layer thickness. We assumed that near surface permafrost thaws, and then to see what is the distribution of the vulnerability to Thaw settlement across Canadian permafrost. So using some of the existing approaches and what we developed, we created some workflows. The idea is that these workflows can provide a step-by-step guide to conduct a desk study evaluation. We tried to combine susceptibility or the methods that are more focused on evaluating changes in the permafrost extent with the approach we created that is mostly focused on settlement susceptibility. We separated these two parts, and following these workflows, one can evaluate both of them separately and then integrate them at the end to have a better understanding of the hazard associated with saw settlement. The process begins with defining the study scope and collecting relevant data, and it ends with some actionable outputs to support planning, for example, identifying areas for future investigation and identifying more source-sensitive areas and comparing development options and prioritizing, let's say, different sites, different roads during planning stage of a project. The other component that we are planning to integrate into this framework is the tools that are mostly focused on estimating saw strain based on site-specific data. So when it comes to estimating saw strain based on site-specific data, empirical tools are widely used. They are easy, straightforward, and they use easily measurable properties like water content and bulk density to estimate saw strain. So here you can see an example of a method developed by Hannah et al., which provide soil-specific correlation for 5 different soil groups. And in this method, volumetric water content is used as a predicting variable. So this is a method that is recommended in the Canadian Foundation Engineering Manual for obtaining saw strain in saw-sensitive regions. Here you can see more examples of these methods. These ones use frozen bulk density as a predicting variable. And just looking at this data and this method, we realized that some soil types are less represented. For example, there were less correlations for peat samples or highly organic soil samples. And also, we could see that there was a large variation in the estimations made using a different method. For example, for a silty sand sample with 1,500 kilogram per cubic meter of frozen bulk density, the difference in the estimation made using different methods can be up to 30%. This was some observation that we made during this literature review, and then we had to obtain laboratory data to be able to develop new tools and also to evaluate the performance of these existing ones and identify tools that were more effective to be integrated into the final framework. So we started with compiling a data set of saw settlement test results, and we were able to identify and collect more than 450 samples. And the data we collected not only included the saw settlement test result, but also sample properties, index testing results, if they were available, and grain size distribution. And the data set represents a diverse range of sample types in terms of the soil group. And the samples are from different regions across Canadian permafrost. So they cover a vast of geographical landscape. So what we did, we kind of digitized any relevant information that we could find in published literatures, in old consulting reports to create these data sets. So for each sample, as I said, we had saw settlement test result, which is basically simulating one-dimensional thawing of a permafrost sample. So in this test, a permafrost sample is thawed under a sitting load, and its deformation is recorded. And once the formation under the initial load is completed, additional loading is applied to develop the full stress-strain relationship for the sample. So for these tests, we plotted the saw strain against vertical stress, like this one, and we also plotted void ratio against vertical stress. So saw strain and void ratio, they easily can be converted. And from these plots, we were able to extract some comparative parameters. So the comparative parameters, for example, here you can see uppercase A naught, which is the source strain parameter, and lowercase a naught, which is the coefficient of volume compressibility. This is what we call comparative parameters, and we extracted these parameters so we can compare them across different soil groups to see the general soil settlement behavior across these soil groups. One thing that I want to mention is that currently there is no standard procedure for conducting soil settlement test results. So the methodology that was used in different sources was different. So again, these approach and obtaining these parameters helped us to make them more comparable and to see the general behavior across different soil groups. So for all the test results, as I said, we extracted these parameters. Here is the distribution of two parameters extracted from soil strain versus vertical stress. So these results show us, let's say, if we divide the samples into ice-rich and ice-poor group, so the A naught, uppercase A naught, or soil strain parameter, is lower for ice-poor samples, here shown in yellow, and it has a higher range for ice-rich samples, which is something that we expected, because in general, this parameter represents the ground ice condition, while the slope of the graph represents the compressibility of the material. And for the coefficient of volume compressibility, we couldn't see that much dependency on sample being ice-rich or ice-poor, but you can see there is a huge difference between values obtained for different soil groups, with the mean value of coefficient of compressibility for peat being about 8 times higher than coarse-grained soils and about 4 times higher than fine-grained soils. So this comparison kind of highlights the critical role of soil type in determining soil settlement behavior, and underline the importance of having more soil-specific consideration in developing predictive tools. The same plot, but for void ratio versus effective stress. So when it comes to void ratio versus effective stress, it seems that a linear semi-logarithmic relationship is the best to idealize these relationships, something that you can see here. And again, there was less dependency on sample being ice-rich or ice-poor when it comes to the parameters related to void ratio at minimal effective stresses, or the ones that are dependent on the ground ice, and more dependency on soil group when it comes to parameters representing of the compressibility of the soils. Here, the compression index of sod soil, which is the slope of this curve. So with this data set, we were able to evaluate how well existing empirical correlations are in predicting the soil strain based on index properties. So what we did, we basically used this data as a test data set to see which methods that are available are doing a better job in predicting soil strain for these samples. And we made sure that the data that we have, they are not used in developing these correlations to avoid any kind of leakage in data, and then seeing the results that were basically based on that data overlap. So in these slides, you can see different boxes. Each box represents a group of methods that use the same predictive variable, and they kind of predict soil strain in a similar sitting pressure. So we grouped them because we wanted to make sure that the predictions made using these methods are basically very close to what we have measured in what was measured in the lab for these samples. And again, the dots in the plots represent the experimental data from the data set we compiled. The lines show the correlations, and the color across all the graphs shows the major soil types. So from this graph, what you can see is there is high scatter in the data. I mean, there is a difference. Like visually, you can see that there is a huge difference between the predictions and the experimental data. And this difference is different for different methods. But I think on high level, you can see the significant scatter in this comparison, which is partially because of the inherent variability in empirical methods. So they are simple, but they are not very precise. So to kind of do a more systematic comparison, we obtained some metrics like mean square deviation and bias. So having these metrics, we were able to quantify the variation in these methods against the experimental data more systematically, and you can see the results here. This comparison showed that the method developed by Nixon and Ladany results in the lowest deviation between predictions and actual soil strengths, and has a bias closer to zero for both coarse-grained and fine-grained soil. It's highlighted in bold in this table. So this kind of suggests maybe using these methods returns a more balanced prediction of soil strain. And also we could see that the other methods, including the one by Hannah et al., which is recommended by Canadian Foundation Engineering Manual, have higher deviation and also higher bias. For some of the soil types, we had more experimental data available to do a better comparison. For the others, the experimental data was scarce, so we were not able to do a good comparison. For example, the data set that we had did not include that much organic soil, but we had many number of peat samples. But on the other hand, for the peat samples, there were less soil-specific correlation developed. And the only method was the one by Hannah et al. And that method did not show good performance. With the data available, we decided to develop some new methods for these less represented soils. And the other thing that I want to quickly go through is the characterization of a stress-strain relationship. I already showed you these plots, and the idea is to obtain the relationship between the void ratio and vertical stress. There was already some work done by Domey and Conrad on fine-grained soil for the focus on obtaining the relationship. So again, with the data available, we focused on the soils that were less represented, including coarse-grained and peat samples. So the idea was to obtain a correlation between the comparative parameters, which are highlighted here, and index properties. So with having the index properties, one can construct the full stress-strain relationship, which is useful for soil strain estimation and for numerical modeling of soil settlement. We focused on coarse-grained soil. For example, we were able to use some of already existing empirical tools for predicting minimum void ratio to predict and to develop some empirical method for predicting sod void ratio. And then we created these kind of graphs that you could obtain sod void ratio at a specific vertical stress, here 15 kPa. And using this sod void ratio and having the compressibility index based on experimental data, one can obtain soil strain at different pressure for coarse-grained permafrost sample. We also tried to use data on index void ratio as a resource for predicting the sod void ratio, but instead of using parameters that are extracted from the grain size distribution, instead we said, what if we only rely on the visual description of the soil? Again, we obtained some values for different soil groups, and then we did a comparison between the predictions made and the measured values using the Thaw settlement data set. In general, this comparison showed that when we compare our methodology with the methods that are already available, the methodology we developed showed a reduced bias and also a reduced root mean square deviation error. In terms of the other group of soils that we focused on were highly organic soil. We had a data set of 17, 18 samples, and we used that data to identify the parameters that were more effective in predicting soil settlement parameters for these soils. So we developed some correlations, and to make these correlations easier to use, we created these simplified charts that one can use to obtain various components of Thaw strain based on water content and other properties like initial frozen bulk density, frozen void ratio, and applied pressure. Because specifically for fine-grained soil, it's really important to account for the applied pressure because of high compressibility, and also it's important to account for a time-dependent component of Thaw strain. So the methods that we have developed for these two types of soil will be kind of integrated into these two sections to create some step-by-step workflows for obtaining Thaw strain or stress-strain relationship based on index properties, or even to idealize, let's say, soil settlement test results to more accurately obtain a stress-strain relationship for further use, for example, for soil settlement estimation or for numerical modeling purpose. And to provide a summary of what I presented, as part of my PhD project, we developed tools and workflows for evaluating soil settlement potential at regional and site-specific scales. The main objective was to enhance our understanding of soil strain and stress-strain relationship across different soil types, and to improve our ability in estimating soil strain. And we tried to create a comprehensive data set of soil settlement test results to support not only our work, but also the future work, because these data sets will be published and will be publicly available. So the idea was to contribute to the geotechnical data for permafrost regions by compiling these data. And future work, like for my project, includes finalizing the framework and the workflows and creating kind of guidelines, something accessible like for final users, which I assume they mostly should be practitioners in the north. And in general, in terms of soil settlement kind of evaluation, I think there is a need for more work on expanding the experimental data that we have, maybe more kind of systematically designed experimental programs. And the other thing is to develop a standard procedure for soil settlement test. This is something that introduces some uncertainty into this assessment. And yeah, with that, thank you so much for your attention. And I will be happy to take any question.
Thank you very much, Zakieh, for a very detailed presentation and sharing insights into your research work. Now I open the house for questions. If anybody has any questions, please direct them to Zakieh.
So thank you so much, first of all, for your presentation and the nice work that you have done. And I know that I have lots of questions. I will bother you afterwards with the questions. But my main question, which might also be from others or just popped up in the other minds, that if you would be able just right now to have all the laboratory equipment to start doing some experimental tests, what would be the first test that you will do? What would be your priority in terms of sediment type? Are you going to start first with working on peat because there are less data? available? And are you going to look at thaw settlement, or are you also going to look at the thaw consolidation? Because as you know, we know that what is going on, a part of it is it's the consolidation that's happening at the same time of thawing. So this is my main question. You have everything that you can possibly imagine in terms of equipment. So what are you going to look at first?
So as I said, I think we already have much more data on fine-grained soil, and obviously because just like you mentioned, we have soil consolidation, which is a complex process, and we want to use those kind of tests to look and characterize that process. But I think highly organic soils, they are also very important. We have huge areas of peat plateaus in Canadian permafrost zones, and these like in these regions, we also have like high ice content. And I think currently we don't have that much of tools that can accurately kind of predict soil strain for these samples. So I think there is a need also to focus on that soil, on kind of that specific soil group. And in terms of the procedure, I would try to use more loading steps. I know there's always a kind of trade-off between the time you spend and the amount of information you get during a test. But maybe I will try to kind of, if the idea is to characterize a stress-strain relationship, I will focus on having more loads, especially loading steps, especially in a range of vertical stresses that are low. And yeah, I think that would be something, because we had some soil settlement test results, but they basically were only using 3 loading steps, and the initial or the very first loading step was kind of already so high that you were losing the whole stress-strain relationship on the lower side of the stress values. And you asked about consolidation versus like soil settlement. So I think the test procedure that we are using is designed to account for consolidation, like because we wait for the sample to settle, for the pore pressure to be dissipated, and then we continue with the next step. So we are trying to make sure that we have effective stress instead of like just relying on total stress, right? So I think every soil settlement test is a soil consolidation test if you give enough time to your sample, like to settle. For some kind of soil types, you need less time. For the others, you need more time. So basically, you have to be you need to just make sure that the timing is enough that you can make sure that if there is a build-up pore pressure, it's dissipated and you have effective stress at the end to have the void ratio effective stress relationship, which is a more common way kind of to like that's something we need at the end for the numerical modeling.
I just have a question about the thaw settlement potential index. So you have the ground ice mapping as the highest weighted variable. You have superficial geology and you have bedrock geology. And so superficial geology and bedrock geology were both used in the ground ice model to parameterize it. And the ground ice model is weighted by far the heaviest. And if you collapse the ground ice map of Canada into 3 classes, it looks nearly identical to the thaw settlement potential index for that reason, because those variables are highly correlated. So I'm just wondering what if you're in a thesis defense and someone asks you what the novelty is of the settlement potential index versus the ground ice map, what you would say.
So yeah, I agree that like soil strain is highly correlated on the ground ice. Like even if we take a look at the experimental data that we have, the majority of settlement, most of the time, is just coming from that ground ice component. And ideally, I would like to maybe in the future, what I would like to do is to use that experimental data to actually differentiate between how much of what portion of the settlement is like mostly related to the like ground ice effect, and how much is related to the like compressibility. I think that I definitely get your point, but I believe that it is just what happens physically. Like the ground ice has a high impact, but there is still some adjustment that needs to be made based on the soil type. Like we have different soil type, different compressibility, just what we saw for the compressibility index or the coefficient of compressibility that are like sometimes an order of magnitude higher in a specific soil type versus the other soil types. So what we did, like to develop that approach, was to kind of look at the surfacial geology types from a different from the perspective of what is the soil texture, what we can interpret in terms of soil texture, and then use that soil texture to do some adjustment on the ground ice impact. Like, because most of the methods that are out there, most of the time they only rely on the ground ice, and sometimes it's not even clear it is ground ice, it is excess ground ice. So there is so much of like not clearly defined kind of terms and properties. But yeah, the idea was just to add more of a geotechnical perspective to that part of the assessment, and also to account for the soil texture, even though it may not look that much significant, but I think there is still value like in including that perspective in the whole process. And for the workflows that we are going to kind of create and refine, the idea is to use soil settlement potential index, like to see how much different soil types that are interpreted from geospatial data are prone to settlement, and then use the other approaches that are more focused on obtaining changes in the active layer thickness, and combine these two together to have a kind of hazard assessment. And the other thing I maybe forgot to mention was to have an approach that is simple and someone can use if they have, like we created this map based on large scale data, like national wide scale data. But if you have a finer scale of data, you still be able to go and use that approach to create a finer scale assessment. Yeah, I agree. I agree that the weight given to ice content is high, but I think it just it's just reflecting what we see like just based on the physical process that goes on. And yeah, I think it would be nice to do more kind of refinement using the experimental data that we have and we compiled. During that time, we didn't have like the information that we have now, but I think there's a value in just doing a comparison and incorporating more of that insight into like the index.
Yeah, it's a good answer. It brings me to another question or comment. So in modeling, you often want to have the simplest model that works well, right? Like you don't want to have extra stuff to make the model more complicated if there isn't a benefit. And I understand the aspect of trying to incorporate that consolidation based on the soil texture in as another layer to account for that geotechnical behavior. But in your model, because it's weighted so low, it actually doesn't seem to affect the results very much. In some areas it might, but in most it doesn't. So, you know, if you want to provide the simplest tool, it may not be needed to have those 2 extra layers that are already accounted for in the ground ice one, even though like I understand the theory behind wanting to do so. Because in the end, like you say, if you have enough data to look at this potential index versus actual thaw settlement information or thaw consolidation information, you could test your thaw settlement potential index and you could test the ground ice model. But if they give the same result, then the simplest tool for any user to use in an initial study would be just the ground ice layer.
Yeah, of course. I think the ground ice is the first thing that you need to have. And
Yeah.
this is the most important thing, of course. But let's say if we have that map that also reflects the soil texture, why someone use the ground ice map when you already have a map? Maybe like there are small
because the ground ice
differences, but
map accounts for thawing and things that happen over a lot of time that the superficial geology does not.
But that's already incorporated in that map because we are using the ground ice map and then we are adding this layer of soil texture.
Yeah.
So I think it's more like a version of the ground ice map that has some adjustments, some like different, like as you said, like for some areas you might see some differences, but it's not that significant in the other areas. So I think if both are available, maybe one can use the soil settlement potential index, but definitely it has like the ground ice map is the basis for that map.
Great. Yeah. Thanks for the great answer.
Thank you very much, Zakieh, and everyone for joining the seminar.
Yeah, thank you, everyone. And and I also wanted to thank you, PermafrostNet, for kind of supporting my research and also for giving me this opportunity to present my work here. Yeah, thank you, everyone.